Welcome to Unit 7, Day 3. In this video, I'll explain to you how to graph an exponential function and also how to write the equation for an exponential function. Let's start with a warm-up that uses some things that you already know. Take a moment to look at these two tables. They each represent a real-world situation, and sketch a graph in the blank space that represents each of these points. Pause the video while you do this. When you press play, I'll show you what I have. So here's what your graphs might look like. You'll notice that I've just shown the x and the y-axis, labeling them with the units from the table. And what you should recognize is that the first graph is a decreasing curve with an asymptote on the right, and the second graph is an increasing curve with an asymptote on the left. These points came from a rough estimate of where the values in the table belong. And what I'm going to teach you about is the difference between the two. In particular, we call this first graph a graph of exponential decay. Remember that in the table, decay is represented by a dividing pattern and growth by a multiplying pattern. But if you just have a graph and you don't have a table, you should recognize the difference between the two because of where the asymptote is. If the asymptote's on the right-hand side, this is called decay. If the asymptote's on the left-hand side, it's called growth. Just for contrast, I've included a third graph. And this third graph, which is talking about someone's age and their height, has a different shape altogether. It's also increasing, so it's also a growth graph. But this one's not exponential. In the table, you notice the difference is that we are adding instead of multiplying. On the graph, what you notice is that it's a straight line, not a curved line. What you should fix in your mind is this middle graph. I sometimes call this the hockey puck shape. If you picture Al Gore's global warming graph, it looks a lot like this. It's increasing slowly at first, and then all of a sudden it increases faster and faster and faster. And that's why we study this, because there are a lot of real-world situations where that fast and sudden increase can cause a problem. Take a moment to summarize what you have understood in these two guiding questions. When you press play, I'll move on to the notes. Here are the notes for graphing exponential functions. You'll notice that we are using the same equation that we used for tables. This equation has two parts. The number out front we call the initial value, and the number inside parentheses, which is the number that has an exponent, is called the multiplier. In just a minute, I'll explain to you how to find those two numbers based on a graph. But let's start with some basic observations about the shape of this graph. First of all, the curve could be facing up or facing down. In my example, this curve faces up, and you can see that it faces up because it's on the top half of the graph. Because my curve faces up, I'm going to know instantly that the A value, the initial value out front, is positive. If my graph were facing down, I would expect that A value to be negative instead. The next thing you should notice is where the horizontal asymptote is. Remember that an asymptote is a straight line that gets very close to the graph but doesn't touch. In my graph, it has a horizontal asymptote on the left-hand side. Because it's on the left, I consider this to be a growth equation. What that means is that the multiplier should be greater than 1. If the asymptote were on the right-hand side, I would expect this to be a decay equation, which means the multiplier would be a fraction or a decimal that's less than 1. The last thing you're going to want to notice is you will need to find what I'm calling a first point. A first point is a point that's very close to the y-axis. In fact, it's exactly 1 unit to the right or the left. This first point is going to help you figure out what the r is. I'll explain how with this example. The first thing you should notice is that the y-intercept, which is 3 for my example, tells you what A equals. And it will do that whether or not A is positive or negative. So you really don't have to think very hard for A. The thinking comes when you try to find the multiplier. To find the multiplier, you're going to go back to that first point, which again is the closest point on the right or the left, and you look for the y value of that point. In my example, it's 6. The multiplier is going to be these two y values divided by each other. You have to think carefully about whether or not you should divide 6 by 3 or 3 by 6. In this case, I chose to divide 6 by 3 because I knew that this was a growth equation, and 6 divided by 3 is a whole number that's greater than 1. If this were going to be a decay equation, in other words, if the asymptote were on the other side, I would have divided 3 by 6 to get 1/2 instead. Let's look at some examples for you. Flip the page. On the next page, take a look at these first two graphs. I recommend referring back to the general observations as you try to write the equation for each graph. Pause as you work, and then I'll show you the answers when you press play. Here are the answers for the first two graphs. Notice that these are both growth equations because the asymptote's on the left, which means both multipliers are greater than 1. The number out front, the initial value a, comes from the intercept, and the multiplier itself comes from dividing 6 divided by 3 or 8 divided by 2, depending on the graph. Let's look at two more examples. Pause the video as you work these two out. When you press play, I will show you the answers. Here are the answers for numbers 3 and 4. Again, you'll notice the first graph is growth. I know that because the multiplier is bigger than 1. It's also facing up, which means the a value is positive, and it is actually positive 1 because that's the y-intercept. The second graph is our first decay graph. Remember that it's decay not just because it's going down, but more importantly because the asymptote is on the right-hand side. When I find that first point, the y value is 2. But instead of doing 2 divided by 1, because I know this is a decay graph, I write the fraction 1/2 instead. Let's do two more. Pause the video as you work out 5 and 6. Be very careful with your initial value for these two. Here are the answers for 5 and 6. What you should notice about these two graphs that are different than all the other ones on this page is that these are both downward facing curves. It's very important to remember that facing down, in other words, under the x-axis, only affects the a value. It does not change the multiplier. Both of these a values are negative because my graphs are facing down. To find the multiplier, we start with the y-intercept and then we find a second point. In this case, although the graph is decreasing, we consider this to be growth because the asymptote's on the left. And so my multiplier is a number greater than 1. This is the example that will most commonly be mistaken. It looks like it's going down, but we consider it growth because the asymptote's on the left. Really, it's a growth equation that's been flipped over by that negative symbol. So it's positive 2 for the multiplier, not 1/2. This is what decay looks like when it's flipped over. It does look like it's increasing, but really it's a decay graph that's flipped over because of the -2 initial value. The actual decay factor or multiplier comes from dividing 2 divided by 6 to get the fraction 1/3. If you were tempted to write a positive 3, pause and go back to my initial explanation of how you find the multiplier. Otherwise, two last examples. Flip the page. Pause the video as you solve 7 and 8. Here are the answers for 7 and 8. That's all, folks.